Welcome to the lesson on force and laws of motion.
We will be able to explain balanced and unbalanced forces, explain the three laws of motion, and explain the law of conservation of momentum.
Please help me. It's not moving.
Do you know why it is not moving?
Yes, because I am not putting enough effort to move this.
Yes, exactly. And this effort is scientifically known as force.
Tell me more about this, Mom.
Force can be explained only by describing what happens when it is applied to an object. Objects move because we apply force on them. A force can be used to change the magnitude of velocity of an object or to change the direction of motion. A force can also change the shape and size of objects.
What happens here? Though they are applying force, why the block is not moving?
Because both of them are applying equal forces in opposite direction. Hence, the block is not moving. Such forces are called balanced forces. They do not change the state of rest or motion of an object. If one of them applies more force than the other, the block will start to move on his side, and then unbalanced force acts in the direction of motion of the block.
That means only unbalanced force makes object move.
Yes, when a man pushes a heavy box with small force, the box doesn't move because of friction acting in the direction opposite to the applied force. The friction force balances the force of push. Therefore, the box doesn't move. However, if the man applies greater force, the box moves because the applied force is more than the friction force. This results in an unbalanced force, and this causes box to move.
Motion states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of force.
What is momentum, Mom?
We know that the impact produced by an object depends on its mass and velocity. A truck at rest does not require any attention when parked along a roadside. But a moving truck, even at a low speed of 5 meters per second, may kill a person standing in its path. A marble, when hits a glass table with high velocity, can break the glass table. Newton introduced this term momentum, which is defined as the product of mass and velocity. The SI unit of momentum is kilogram meter per second. The force necessary to change the momentum of an object depends on time rate at which the momentum is changed. The second law of motion is often seen in action in our everyday life. Have you noticed that while catching a fast-moving cricket ball, a fielder gradually pulls his hand backwards with the moving ball? In doing so, the fielder increases the time during which the high velocity of the moving ball decreases to zero. Thus, the acceleration of the ball is decreased, and therefore the impact of catching the fast-moving ball is reduced. The second law of motion gives a method to measure the force acting on an object as a product of its mass and acceleration.
Can we prove this expression, Mom?
Let object of mass m is moving with initial velocity u and final velocity v in time t. F is the constant force applied throughout the time t. The initial and final momentum of the object will be P1 equals to m into u and P2 equals to m into v respectively. the change of momentum is directly proportional to difference of P2 and P1, which is nothing but m into v minus u. The rate of change of momentum will be proportional to m into v minus u upon t. As rate of change of momentum is applied force, hence applied force
on another object, there is a pair of forces and not just one force. These are opposing forces and are called action and reaction forces. When a gun is fired, gun exerts forward force on the bullet and the bullet exerts equal and opposite reaction force on the gun. This results in recoil of the gun. When a sailor jumps out of a rowing boat, then an equal force on the boat moves it backwards. Newton's third law of motion states that to every action there is an equal and opposite reaction and they act on two different bodies. To understand more about this law, let us do an activity. Take two spring balances connected with each other as shown. Balance B is fixed with a rigid support like a wall. When force is applied through free end spring balance A, it is seen that both spring balances show same reading on their scale. This means that the force exerted by spring balance A on B is equal but opposite in direction to the force exerted by balance B on A. Hence, we can say that for every action, there is an equal and opposite reaction.